reminder. So you had, not really reminded. So you had the first class or labs or tutorial, whatever you call it, with the GTA, right? This week. So you had this with Yang. There are 2 GTAs. There is Longfei as well. So I think this week was Yang. Probably next week you will have Longfei. Hope this was helpful, right? Make use of this time. Feel free to ask questions also. You're gonna have, this is very helpful for you to really get your hands dirty and start, you know, solving problems and implementing on MATLAB all what we have talked about during the lecture. So hope this was helpful. Feel free to send me any comments or suggestions, things you would like to do, things actually you think should be done differently. That's always helpful to us. Right, so other things, so you're gonna have the first coursework, reminder, the first coursework, the deadline is Sunday, 7th of February at midnight. So you have next week to work on it. If you haven't started yet looking at the problems in coursework 1, you will see it's not very difficult. Coursework 1 is just to make sure that you're all at the roughly same level. You understand those really fundamentals, but don't leave it to the end, right? Good. Otherwise, let's continue. So today is our lecture number 4, and we started playing with multiple antennas, with MIMO, multiple transmit, multiple receive antennas in our last lecture, last Thursday. And what we did, we started looking at the MIMO case. So we have this relationship, right? This multiple input, multiple output relationship, where this is actually a vector. C of k prime here is a vector, and potentially could be a matrix, right? Because for each time k, essentially you have a vector. And so what we looked at, we looked at the case where we don't know h at the transmitter. So that's what we finished with last week, and we already knew a little bit about this before, because we said we've seen what Alamouti coding is, and we saw that you can achieve some diversity gain even if you don't know h at the transmitter, right? And we have done this for the MISO case, signal receive antenna. We have done this for the MIMO case when you have multiple receive antennas. And the multiple receive antenna is just here reusing the classical Alamouti schemes, but when you have multiple receive antennas, and so you end up with a diversity gain that is equal, given by 2 multiplied by NR, right? And this is what we have here, right? And the reason for this is because essentially you have 2 NR coefficients, independent coefficients in your channel matrix H, right? So this is what we did last week. We finished with this last week. So today, what we're going to do is that we're going to continue with this basics of MIMO, point to point. So one transmit, one receive, one transmitter, one receiver, multiple transmit antenna, multiple receive antennas. But the next step now is to try to understand what can we do when we know the channels of the transmitter. We know the channels of the receiver, but we know it at the transmitter as well, right? So what can we do, and how does that compare with the Alamouti schemes? Remember what we did for the MISO case. The MISO case, we had some form of maximum ratio transmission or match beam forming, right? We were beaming in the directions of the channel because we had knowledge of the channels at the transmitter, right? And that gives us some gain over the Alamouti schemes. When we had a MISO system, we had the same diversity gain, but we had an array gain. So we had an array gain because we had knowledge of the channels at the transmitter, and that gives us, you can view this as a kind of beam forming gain, if you like, right? So we'll see something similar now in the MIMO case when we have multiple receive antennas. And so the first thing we're going to do is to extend this notion of match beam forming or maximum ratio transmission from the MISO to the MIMO case, right? So in the MISO case, we had something like this: y was equal to h w c plus n. and we were choosing W as H Hermitian divided by the norm of H, right? Very reminiscent of what we did with maximum ratio combining, right? Maximum ratio combining essentially maximize the SNR. You receive the SNR. You can view this as a form of actually match filter. And here, what you do is that you do the same thing, but at the transmitter. So you maximize the SNR by matching the precoders to the channel vector, right? How can we do the same thing or something similar to that when we have matrices? So now I have still a symbol C that I want to transmit. I still precode with W, right? But now instead of having a vector channel, so this was NR by 1 vector in the MISO case. Now here I have NR by NT. Sorry, NR by 1. It's a MISO, so it was 1 by NT, right? 1 receive antenna, right? Now we have NR by NT, right? We have multiple receive antennas. That means actually we have multiple observation in our received signals. We have Y is a multi-dimensional vector, dimension NR, right? And we have a Gaussian noise here, AWGN noise, right? So covariance matrix is scaled identity. Right, so what can we do here? If I have multiple observations, right, what can we do? We can already process those multiple observations. I can combine them, right? So I can have a combiner G, a bit similar to what we had when we were doing, the combiner when we had the SIMO case. Remember, in the SIMO case, we had something like this. We had Y was H, C plus N. This was a vector. This is a vector. This is a scalar. This is a vector. And then we were applying a combiner here, G, G, and G, right? And one of those combiners was maximum ratio combining, right? So here you see that you have a precoder W, but now you can apply a combiner. So you have the combination of the two, the precoder on one hand and the combiner on the other hand, right? Now, if I have AWGN noise here, how can I choose my combiner G to maximize the SNR? What I would do is I would use maximum ratio combining. So I can choose G according to the maximum ratio combining design that we had earlier on, and G here was proportional to H Hermitian, right? Simply, right? So I can do something similar here. What I can do, I can choose G so that I will maximize the SNR of this transmission. What is my effective channel that G has to operate on is these precoded channels here, right? H multiplied by W, H is NR and T, and W is NT by 1. So this whole thing is NR by 1 vector, effectively. So what I can do, I can apply G on this effective channel that is given by H multiplied by omega, right? We'll come back to this here, but this is what we do here, right? So how do you design your combiner? You have an effective vector H now that is equal to that. That's my effective channel. And now I take the Hermitian of that effective channels. This is when we do MRC, right? That maximize the SNR. I can do the same thing. My effective channels is HW. So now I will take the Hermitian of HW to design G. That's what we have here. I choose G as a maximum ratio combiner. Right. Now if you do that, I have G, H omega. G is H omega H. So this is equal to omega H, H Hermitian, right? And so this is my G. This is my G. Here. Right. And I have HW, right? So now as you see that you have some form of quadratic form here, you have a W on the right side, on the left side, and then you have H Hermitian H. Right? What is this? this is actually a Hermitian matrix, and I can do an eigenvalue decomposition of this. If you have, you know, Hermitian matrix and you do an eigenvalue, remember what we had here in the last lecture. We said we can do an eigenvalue decomposition. I'm going to have right eigenvectors, left eigenvectors, and you're going to have a matrix of eigenvalues, right? So let's do this eigenvalue decomposition. If I do that, I simply write this. This is my H Hermitian H, right? Okay, so how can we write this slightly differently? Let me add a page here. Right, so let's take an example. Imagine I have H is a 2 by 2 matrix, right? So H Hermitian H is still a 2 by 2 matrix. So I can write VH, and let me take the same notation as there. Right. This is also called lambda H, if you like. VH Hermitian, right? This will be a 2 by 2 matrix. This will be a 2 by 2 matrix. This will be a 2 by 2 matrix. This will be a diagonal matrix. Right. So I have a 2 by 2 matrix, and now I multiply here by W on the right side and by WH on the left side. What is W here? Is a 2 by 1 vector. What is WH here? Is a 1 by 2 vector, right? So this whole thing essentially here is a scalar, right? So if I have this, if I look at this here, I take my W and I multiply by essentially the eigenvectors, all the eigenvectors that we have in that matrix. Right? So I'm going to have two eigenvectors like this, and I do the transpose. So that's going to be V1, and then that's going to be V2. Those are the two eigenvectors that I have in this matrix. And I multiply by W. So what I end up with, I'm going to have W multiplied by V1 Hermitian and W multiplied by V2 Hermitian. So if I write this down here, I'm going to have V1 Hermitian multiplied by W. I'm going to have V2 Hermitian multiplied by W. That's going to be this matrix there, right? Here, I'm going to have what? I'm going to have the transpose of that. So I'm going to have V1 Hermitian W, V2 Hermitian W, and I take the transpose of that. So this is going to be a 1 by 2, right? And now I have here I have a 2 by 2. I can write this sigma 1 square, sigma 2 square, right? This is a diagonal matrix, 0 and 0, right? So this is a scalar, essentially. This relationship here is a scalar. And so if you multiply, if you calculate this, you're going to have this will be multiplied by this, will be multiplied by this. This is actually the conjugate of that. So that's why I'm going to have the magnitude square of that quantity and multiply every time by the corresponding sigma square, right? This will be multiplied by that, will be multiplied by that, and that's going to be the second contribution. So this is going to be equal to sigma 1 square V1HW square plus sigma 2 square V2HW square. Right. Now, if you think about this, what is our W here? This is a unit norm vector, right? Is normalized. Remember when we had the MRT, maximum ratio transmission, we had this, right? So what that means is that here, the norm of W is equal to 1, right? The norm of W is equal to 1. And I always normalize with respect, normalize W so that is equal to 1, because I need to maintain a certain average power constraint at the transmitter. Right, so that means actually now my precoder here, my W here, has also a unit norm equal to 1. Right, so the norm of W here is equal to 1. Square or not square here does not change anything, is equal to 1. What are the norms of V here? Right, they have a certain norm as well, right? And what's going to happen here is that if I choose W1, W, that is such that is more aligned to V1 or more aligned to V2, I will favor more this term, or I will favor more this term, right? V1 and V2 are two orthogonal vectors, right? So if I have my W here, I can orientate more towards V1 or more towards V2. Which one should we try to tweak towards towards V1 or towards V2 will depend on whether sigma 1 is larger than sigma 2 or the opposite. So let's imagine that I have those eigenvalues are ordered in descending order. So I have sigma 1 square is larger than sigma 2 square. So this term here, this will be larger than that, right? So that means actually I should try to maximize this term here because my return on investment will be larger because this coefficient is larger, right? So I should tweak W towards V1. If I take W equal to V1, this term here will be maximized because this one will be aligned with this one. This one will be equal to 0. But that's okay because I will put all my energy essentially towards V1 because sigma 1 square is larger than sigma 2 square, right? So this is what you see, that the maximum value you can achieve here will be actually equal to sigma 1 squared, the maximum eigenvalues that you have in the systems. And so this is what we have here in general, not when you have a 2x2 system, but you have NR receive antenna, NT transmit antennas, and you have the rank of your channel matrix in general could be given by rank of H here. So you may have 0 eigenvalues essentially. Well, your maximum here, the maximum of this quantity is always equal to the maximum eigenvalues. And how would you achieve that equality here? Is by choosing W to be aligned with the dominant eigenvectors of H, right? So you choose W to be equal to the dominant V. So the V that correspond to the strongest eigenvalues of this matrix H, right? So if you write this in decreasing order, you're going to have sigma 1 will be the strongest single value eigenvalues, and so you're going to choose V1 as the dominant eigenvector, and so you will transmit along that directions, right? So this is what we do, and this is why we have this here. You transmit along the dominant eigenvectors of H. Right, so if you do that, what's happened to G? Well, then you have this relationship here, and now you know W, you know that is equal to the dominant eigenvectors of H, or the dominant right singular vector of H, and so you can compute G. So G, what is it? Is, again, that is W Hermitian, right? And so now I know W is equal to Vmax, so I'm having here. I can take this singular value decomposition, right? Remember, H will be a UH sigma H VH Hermitian, and I take the Hermitian of this. And so what I'm going to have here is that this quantity here, this is a matrix, VH is a matrix that is given by, let's say, V1 all the way to V whatever dimensions I have here, right? So I have multiple singular vectors, and I take one of them is the Vmax. So let's imagine V1 is the dominant one. So let me call this V1 is equal to Vmax, is a dominant singular vector. I will match this with V1. So when I do the inner product here of Vmax Hermitian with VH, what I'm going to have is inner product Vmax with V1, I'm going to have 1. And then the other one will be equal to 0 because Vmax will be orthogonal to all the other eigenvectors. So we're going to have a vector of 1 and then zeros, right? Vector of 1 and zeros multiplied by these quantities will be equal to the dominant singular vector values of sigma H, the first one, multiplied by the dominant left singular vector of H, and that's this. Okay, so what that means is that here this is called dominant eigenmode transmission. You actually have multiple modes here. You could transmit from here. in this 2x2 example, you have two modes. You can transmit more towards V1 or more towards V2, but we choose to transmit more along V1 because V1 corresponds to the strongest eigenvalue. So you have a 2x2 matrix, and what you do, you transmit along the right singular vector of H, V max, and you combine along U max here, which is the dominant left singular vector of H. So you do a singular vector decomposition. You have H, and you transmit along V max here. You transmit along V max here, C. That's your precoded information, and you combine here along the Hermitian of U max, the left singular vector of U. Okay, so this is what you do, and by doing this, essentially, you will decompose your H matrix into multiple modes, but you will take the dominant one, the one that corresponds to the dominant eigenvalue, right? This is what is called dominant eigenmode transmission. Okay. So if you have a single receive antenna, well, in that case, you don't have, multiple eigenvalues here because you have a vector channels has a rank 1, so you have only one eigenvalue, and so in that case, you can easily show that your dominant, your dominant right singular value, a singular vector here, is nothing else than the H, the channel itself, or actually the normalized channel, if you like, right? So if you have only a single receive antenna, choosing this relationship boils down to simply transmitting along the channel direction. Okay, so the dominant eigenmode transmission is actually more general than what we did before with the match beamforming maximum ratio transmission. In the case where you have single receive antennas, this quantity simply boils down to that, right? That's a good exercise you can try at home just to get a bit more familiar with those singular value decomposition. Right, so this is a very important thing that enables you to maximize the SNR of this transmission when you have a MIMO case. And so effectively, what you get after you're doing the combiner on the right side, the precoder on the right side, the combiner on the left side, you get an effective channel gain that is proportional to the singular value of this channel matrix H or the eigenvalue of the channel matrix. And you have a noise here. This is actually a noise that is simply your combined noise that has a certain variance as well. And so what you can show, I will not do that because that requires some more advanced probability. But essentially, you can show that this gain here, so this dominant eigenvalue, will depend on the statistics or I would say the distribution of the channel gains, right? And you can show that this quantity actually, this quantity here, will actually depend on the rank of this, the distribution of this, but typically this quantity is actually between NT and R and the maximum between NT and R. So either between the products of NT and R and the maximum between the two. Right, so if you have NR is equal to 1 here, if you have NR is equal to 1, you have the MISO case, you see that your GA is between NT and NT, right? So your GA is equal to NT. This is what we have seen already before. When you do maximum ratio transmission, you have indeed that your received SNR after precoding is actually NT times what you would get if you had a single antenna, right? If you have multiple receive antenna, this gain will really depend on the structure of this channel matrix, but typically the gain is ranged between those two extremes. What you can show as well, and it's a bit more complicated, is actually you also end up with a diversity gain that is equal to NT and R, which is if you have two transmit antenna with Alamouti, you remember we had 2 NR. That's the diversity gain we get with Alamouti. Right? So here, if you have two transmit antenna and you do dominant eigenmode transmission, you would end up with the same diversity gain as Alamouti. The difference with Alamouti again is that you're going to have an array again here because you have knowledge of the channels at the transmitter that enables you to do some form of beamforming. When you pre-code along W here, you actually do some beamforming along some directions, and those directions are given by the dominant singular vector of H, dominant right singular vector of H. Right. If you have more than 2 transmit antennas, in general, you get NT multiplied by NR, right? With Alamouti, you're restricted to 2 transmit antennas, so you cannot get beyond 2 transmit antennas. I will show you some schemes later on that enables you to go beyond 2, but you see you're going to have some other issues arising. Okay, so here, if you have 2 transmit antennas, dominant eigenmode transmission will give you the same diversity gain as Alamouti, assuming again we have IID relay fading channels. But the dominant eigenmode transmission will give you an additional array gain. And so similar to what we had before, you're going to have the same slope, but you're going to have a shift of the curves to the left. This is your dominant eigenmode transmission. This would be the Alamouti scheme. Okay, so you will see this. You will play with that also. Right, so can we do something better than that? Can we do something? This is interesting to maximize the SNR. But you could argue, yes, but there is something we don't make use of here. Any idea? Right, we transmit along the dominant eigenmodes, right? So we pre-code along the right singular vector, dominant right singular vector, we combine along the dominant left singular vector. But we don't make use of all the other singular vectors, right? Actually, VH here, or if I take this decomposition, I have multiple of them on the right side, I have multiple of them on the left side, right? All those columns here of UH, they're all orthogonal to each other, right? All the columns of VH, they're all orthogonal to each other, right? So what happens is that effectively, if I do that, what does that mean? I have some kind of virtually, I have H. I can view this as some form of directions here. Let's imagine my H is a 3 by 3 matrix here, right? U of H give me maybe 3 directions on the receive side. Then I have 3 eigenvalues or singular values here, 1, 2, 3. And on the right side, I have multiple directions as well, given by the right singular vector, right? That's what I can imagine. That goes from the transmitter to the receiver here, right? If I qualitatively represent a little bit what's going on inside this channel. And so I have 3 of them. This is sigma 1, sigma 2, sigma 3. And what we have done so far is say, let's use the strongest one to maximize our SNR. And so if I use the strongest one, I take my transmit symbol C, and I transmit along one direction here, the dominant right singular vector, and I combine along that one, right? And so I use a virtual path here, which is along the dominant eigenvectors, singular vectors, the right and left singular vectors of this channel. But I have 2 and 3 there. And actually, those 2 directions are orthogonal to each other. So actually, that means that if I can pre-code another information along this one, and combine along that one and that one, I may actually end up with transmitting 3 streams in parallel. One stream that goes along the dominant one, but I can still transmit some information along the weakest one as well, right? That's where the whole MIMO benefit starts to kick in. You realize that now you have a channel matrix that has multiple eigenvalues, multiple kind of eigenmodes, and instead of transmitting only on the dominant eigenmode, you transmit along multiple of them. You try to excite each of those eigenmodes, and because those eigenmodes are actually orthogonal to each other, they will not interfere with each other. If I transmit a symbol C1 through this route and a symbol C2 through this route, those 2 symbols will not interfere with each other because of the property of the SVD. The columns here of U are orthogonal with each other, the columns of V are orthogonal to each other, right? So what is this called? This is multiple eigenmode transmission. right? And you will see that actually this is a key to achieve the capacity of the MIMO channel. So let's imagine now I have a certain number of receive antennas, certain number of transmit antennas. Let me choose 2 for simplicity, but you can do this for any dimension. I will give you some example with 2. So you have now your channel matrix H still. I have a vector here, C prime, and before we had C prime was given by essentially V max multiplied by C, right? Now my C prime will be slightly different. Instead of having just V max multiplied by scalar, and now I will have the right singular vector, the right singular matrix, so I have U, H, sigma H, VH, Hermitian, right? Now I will precode along VH, the entire matrix, this is what I have here, and I will use now a vector of stream. Instead of having a scalar like what we had just before, the dominant eigenmode transmission, now I have a vector. So imagine you have a 2 by 2 scenario. You have 2 by 2. Right? If you have a 2 by 2, you have your VH is a 2 by 2 matrix, right? So your VH multiplied by C, and C now is this here is a 2 by 1 vector. I will transmit 2 streams, right? This quantity will still be a 2 by 1. So this actually will be similar to what we had here. This was a 2 by 1 also in the case where we have 2 transmit antennas. But now what that means is that I have VH is a V1 and a V2, right? And so I have multiplied by C, which is C1 and C2. I'm going to have my transmit signal, C prime, VH multiplied by C, will be V1 multiplied by C1 plus V2 multiplied by C2. What does that mean? I transmit C1 along a certain direction, V1. I transmit C2 along another direction, V2. So if I have my transmitter with 2 transmit antennas here, it says that I transmit C1 along a certain direction here. C1 goes into that direction, and I transmit C2 along another direction. Right? That's what it means. Right? Right. So now I transmit multiple streams along each of those right singular vectors of my channel matrix H. How do I choose the combiner G? I have multiple streams that I transmit. So now I have a combiner that is not just a vector, it's a matrix. It's a matrix that is given now by the left singular vector of H, right? And is given by the Hermitian of this. So what does that mean? I now transmit here H, right? Let me take this example. I have C1, C2. I transmit along VH. I have H. And now I have here UH Hermitian, right? And so this is my observation Z. And I have some noise here after combining. Good. This is still a vector, right? My U here is a 2 by 2 matrix, so this is a 2 by 1 vector. This is a 2 by 2 matrix. This whole thing now is a 2 by 1. Right? Now, if I look at this here, if I take SVD decomposition, I have UH, sigma H, VH Hermitian. And now I have this multiplied by UH Hermitian and VH. Right? What do we see here? Well, you see something quite nice and not so surprising, because you transmit along the right and left singular vector. This is identity matrix. This is identity matrix because the right and left singular vector matrix actually are unitary, right? So this is identity matrix. So what that means is that now I have a system model effectively that writes Z is equal to sigma H multiplied by C1, C2, plus some effective noise, right? In other words, I write this one step further. I have Z1 and Z2 are my two observations. I have sigma 1, not square here, sigma 1. I have sigma 2, right? I have 0, 0, C1, C2, plus some noise, right? So I end up with two observations. Z1 is sigma 1, C1, plus some noise. Z2 is sigma 2, C2, plus some noise, right? I transmit two streams, and I get two observations. And you see that those two streams do not interfere with each other. I can do a maximum likelihood detections on the first observation in order to get C1. I can do a maximum likelihood detection on the second observation in order to get C2, right? Those two streams do not interfere with each other. I have two transmit antenna, two receive antenna. I'm able to transmit two streams of information, and those two streams do not interfere with each other. Very nice, very low complexity. The drawback with this is that, of course, you need to know H of the transmitter, because you need to be able to do this SVD. So you need to know always H of the receiver, but H of the transmitter as well, so that you pre-code along VH and you combine along UH, right? So now you have two streams that actually really travels through those two virtual paths that I have now two virtual paths, a sigma 1 and a sigma 2. And I'm saying my C1 here, let me write this in red. I have C1 travels through this, and I have a C2 that will travel through that. And they will not interfere with each other through those virtual paths in this MIMO channel, right? Quite nice. So what is the benefit of that? You can imagine, now I have a certain spectrum, but I have two streams that are transmitted at the same time on the same frequency, right? So I can increase the amount of data that is effectively transmitted, and so the spectral efficiency, because I transmit two streams at the same time. Right, so this is the main benefit of one of the benefit of MIMO, and the main benefit compared to the MISO and the SIMO. The MISO and the SIMO, you cannot do that because you always have only one singular value. You can do this only once you have multiple singular values. So that means that my matrix here of singular values, well, I have to be careful. If the rank of this matrix, this one here is nothing else than what I had here, right, is this, right? So I have diagonal entries, but if some of those diagonal entries are equal to 0, that means that on my path here, let me take those example of three here, right? Imagine that I have three singular values, but one of them is equal to 0. That means actually I cannot use that virtual path because the gain here will be equal to 0. If I transmit anything along this path here, because that singular value will be equal to 0, I will lose that information, right? It will never appear at the receiver. I'm going to have 0 at the receiver, just noise, right? So the number of streams that you can transmit will be at most equal to the rank of that channel matrix H, right? So if you have NR receive antennas, NT transmit antennas, what's the maximum rank that you can have? Well, the rank of H will be equal typically to the minimum between the number of transmit and the number of receive antenna. Could be lower than that, right? So it will be at most equal to the minimum between the number of transmit and the number of receive antennas. If you have rank deficient matrices, so if you have 3 by 3 matrices, but you have the columns or the rows are linear combination of each other, you're going to have only one singular value that is non-zero, and you have only one path that you can transmit information to, right? But if you have well-conditioned matrix H, that means actually the rank is as high as possible, so equal maybe to the minimum between NT and NR. Then you could potentially transmit multiple streams in parallel, at most the minimum between NT and NR. Good. So now in terms of rate, what does that mean to have that here, right? So imagine you have a certain noise now, and you have a certain channel gain, right? So I will have now a rate that will be proportional to my signal to noise ratio here. my signal-to-noise ratio will be essentially the square of this. So that will be the eigenvalues of my channel matrix divided by the noise power, right? And this is what we have here. I have essentially a long-term SNR multiplied by the eigenvalues of the channel K, of the virtual path K, or the mode K, right? And I'm allocating here a certain power to that virtual path. So from an information theory perspective, now imagine those are not finite constellation. Those are Gaussian inputs, right? This is actually a SISO system, effectively SISO system. So what's going to be the rate of here? The rate will be a log2 1 plus SNR, right? So the SNR here will be a long-term SNR multiplied by the strength of this channel gain, multiply here by the power that I allocate to that stream. And let me call it S1 square, for instance, right? That's the power that I allocate to that stream. What I have for the other one will be actually the same, but I'm going to have sigma 2 S2. So here I have two streams. So my rate, the total rate, will be a log2 1 plus rho sigma 1 square S1 square plus log2 1 plus rho sigma 2 square S2 square. This is the rate of the first stream. This is the rate of the second stream. They do not interfere with each other, so I can really sum the rate of each of those streams, right? Now I have S1 square, S2 square. We have to be careful. I have still one transmitter. That means actually I have a power constraint that is actually at the transmitter. My power constraint now says S1 square plus S2 square is essentially equal to 1. It means that S1 square is the fraction of the transmit power that I'll allocate to the first stream. S2 square is the fraction of the transmit power I allocate to the second stream. And I can change this power allocation among those two streams in order to increase the rate of the transmission, the total rate of the transmission, right? So this is what we have here. Here I denote with SK, so let me change this. So my power will then be S, okay? Right. So the power, the fraction of the power is S. So if I use S1 is equal to 1, essentially I put all my transmit power onto the first streams. So all the power goes to here, so I don't transmit anything on the second one. Inversely, if I put S2 equal to 1, I don't transmit anything along sigma 1, I put everything along sigma 2. Right. Right, so if you have a certain rank, if the rank of my matrix now, if I rank H, it means that my rate in general will be a sum for n equal to 1 to the rank of H of a log2 1 plus rho sigma k square sk, right? And what is not k is here, right? So those actually the non-zero eigenvalues of H, right? And I have a number of them that is equal to the rank of H, essentially, right? So each virtual path or each mode that has a non-zero eigenvalues potentially can contribute to a rate, and what will be the value of that rate will depend on how much power I allocate to each of those virtual paths, right? Okay, is that clear? Hope it is. It's a very important notion. We're going to play with this quite a bit. Right, so what you expect is that if your rank here increase, you can hope that your rate will increase more quickly with the rank of H, right? Imagine if I simplify a little bit for the time being so that you start seeing some of the concepts that will arrive. But imagine I have sigma k is positive, right? They're always positive. Those are the non-zero eigenvalues. that I consider in this equation. And imagine Sk is positive as well, right? And let's imagine that now rho tends towards to infinity, right? So I fix the fraction of the power that is allocated to stream 1, stream 2, stream 3, and so on. But my long-term SNR is actually increasing, right? So what that means, I can say roughly this quantity, roughly this is equal to rho Sk sigma k squared, right? If rho is sufficiently large, right? So I'm gonna have the rate now is a sum of log 2 rho Sk sigma k squared is k from 1 to the rank of h. So I'm gonna have here rank h multiplied by log 2 rho plus a sum over k of log 2 Sk sigma k squared. Good. What does that mean? This is a constant, not function of rho, not a function of this long-term SNR. And here that I have is a pre-log factor of the rate, right? The log is here in dB, in log scale, so in dB. And the pre-log factor of the rate is the rank of h. So what that means, if I draw rate versus log 2 rho, it means that the slope of the rate versus the SNR is proportional to rank of h. Right? If I can increase the rank of h, at high SNR, my rate will increase linearly with the SNR, and the higher the rank, the higher the increase. So the rate here, the rank here, can be viewed as the slope of the rate versus the SNR at high SNR, right? This is why it's quite important to increase this rank, because at high SNR, it means that potentially you can have, if you increase your SNR by 3 dB, your rate will increase much faster if the rank of h is large, right? So this behavior, this slope there, this is what is called the multiplexing gain of MIMO. And if you have SISO, SIMO, MISO, the rank of h is always equal to 1 because you always have scalars or vectors, right? So your rate increase relatively slowly with the SNR. In the MIMO case, because your rank here will be typically large, or you hope it's large, the rate will increase much faster with the SNR. And this is called the multiplexing gain. It's essentially the number of interference-free streams you can transmit in the system at high SNR. Good. So, right. So we'll come back to this multiplexing gain, but there is an important question that we had here is, I said this is a fraction of the power allocated to those two modes, right? But the question is, how should I allocate this power? Should I always allocate power to those two modes? Or does it depend on those values here, sigma 1 square, sigma 2 squares? And does it depend on rho, right? So that's a very important question. If you want to maximize the rate, you want to have the highest possible rate, how should you allocate the power among S1 and S2, right? So that's a question we have here. So the question is the rate achievable in a MIMO channel with multiple eigenmode transmission and uniform power allocation? So I split my transmit power uniformly across all modes. So if I have two modes, I put half of the power on mode 1, half of the power on mode 2. Is doing this giving you always a larger rate than dominant eigenmode transmission? So dominant eigenmode, remember, you transmit only on the dominant one, on the strongest one. So if you split your power uniformly among the two modes, does that give you better rate than transmitting always on the dominant one? Very important questions. And the answer is no, right? And you can understand why. Let me give you this example, what we had here, right? Let's imagine that I take S1 is 1/2, and S2 is 1/2, right? So if rho 2, or sigma 2 here, is non-zero, but if it's very weak, let's imagine is very weak, so I allocate some power, but it's very weak. So the rate of that stream will actually be very small, very, very small, right? And I might be better off to actually allocate more power to the stronger stream. If I allocate half of the power here, but the contribution to the rate is very small, effectively my rate will be roughly equal to the rate of the first streams, but I use only half of the power, right? If I do dominant eigenmode transmission, I transmit all the power to the first one, the strongest one, I allocate 0 power to S2. But this may be a good situation if indeed sigma 1 is much larger than sigma 2, right? In that case, I would not waste any power on any channels that anyway is very weak, right? So you can see that intuitively, allocating power uniformly is not always a good strategy, right? Allocating power uniformly may be a good strategy if you really had high SNR, because then you will see that you're going to have indeed the rate will increase with the rank of H. But if you have a finite SNR, sometimes this quantity may be very, very small, will not contribute much to the rate. And so you may be better off to transmit only to a subset of those eigenvalues or a subset of those modes. Okay. So, so this is what it means. If you have two strategies, uniform power allocation and dominant eigenmode transmission, be careful. It does not mean that transmitting more streams, multiple streams with uniform power allocation, always gives you higher rates. It will really depend on the SNR, and essentially the strength of your eigenvalues. Right? So you can have both. The uniform power allocation could be larger than the dominant eigenmode. You could have the opposite as well. Right. So the question we're going to answer later on is, okay, but how should I allocate? What is the optimal power allocation for SK in order to have the best possible rate performance, right? That will always outperform uniform power allocation or equal uniform power allocation, and always outperform dominant eigenmode transmission or equal eigenmode transmission in some scenarios, right? Right, so this is the notion of multiplexing gain that I mentioned already a bit, right? So we have array gain, diversity gain, we're gonna have the coding gain as well, we'll see this. And those actually quantities of benefit that you see in SIMO, MISO, and MIMO as well. So you still have the diversity gain, the array gain, the coding gain in MIMO case. But additionally, you have what I mentioned earlier on is the multiplexing gain. And this is this ability to transmit multiple independent streams and interference-free streams in these MIMO channels. And this is measured high SNR that is given by the ratio between the rate and the SNR in dB. And you look at this ratio when the SNR grows to infinity, right? So here, in the example, in the equation I had here, right? This is my rate, is a function of my long-term SNR, right? If I look at the limit when rho goes to infinity of rate rho divided by log 2 rho, right? I'm gonna have rank of H here plus a quantity that I may call A here, A divided by log 2 rho. A is a constant independent of rho here, so this will go towards 0. And so I'm gonna have here in this example where I have the eigenmodes are positive, I allocate a non-zero fraction of power to all of them. I'm gonna have a multiplexing gain that is equal to the rank of H, right? So this will be called this G of S. Will tell you essentially the number of interference-free streams that you can transmit in these systems, and the rate at high SNR will be directly proportional to this number of interference-free streams that you can transmit, right? But the high SNR, you can view this as the pre-log factor of the rate, so it's the slope of the rate versus SNR, right? And different schemes may have different multiplexing gain. What would be the multiplexing gain of the dominant eigenmode transmission, right? You transmit only one stream, right? So there is no way you can have a multiplexing gain that will be equal to the rank of h. You're going to have a multiplexing gain that will be equal to 1, right? That's it. So in that case, you're going to have simply at high SNR, the rate will be log 2p plus something, right? But the slope will be relatively low. The slope will be low here, so that's going to be dominant eigenmode transmission. And this one here could be your multiple eigenmode transmission, higher slope. Right, multiplexing gain, very important. And typically is a measure at high SNR. You can measure it at finite SNR, the slope of the rate versus the SNR, but it is easier to see it at high SNR. Right, so at high SNR, essentially you can view this. You always have plus some terms here, but this is will be not a function of the SNR. So you have this, and so the maximum multiplexing gain you could have, your G of S here, will be smaller or equal to the rank of H, right? If you do multiple eigenmode transmission and you do it well, then your multiplexing gain will be equal to the rank of H. If you do suboptimally, like you do, for instance, dominant eigenmode transmission, your multiplexing gain will be smaller than the rank of H. Right, now you see that the rank of H is very important, right? Because that will determine essentially how many streams potentially you could transmit in parallel with each other. And how is this rank of H a function of the physics of the MIMO channels? Well, it turns out the rank of H will be a function of essentially how all those different coefficients, if I have my channel matrix and I have a 2 by 2, and I have H11, H12, H21, H22. The rank of H will be a function of how those different coefficients actually relate to each other. If I have linear combination of those columns or those rows, I'm going to have rank deficient matrix. And you can imagine that actually if you have more correlation between those elements, then that means actually statistically speaking, you may have actually the rank will be actually decreased, right? So you can characterize the statistical properties of this channel matrix H, and you can model this, and this will give you some insight into the ultimate performance of MIMO systems, right? So let's do that now. So we're going to look at how we can model this MIMO channel matrix, try to dig a little bit more into this relationship between those different coefficients, and then we will come back. We will come back to this kind of expression, and we'll try to figure out how we can actually allocate the power to those different eigenmodes to try to maximize the rates. Right. Any questions so far? Yeah.
Sorry, Professor Bono, I have a quick question about the multiplexing gain. Are we talking the same thing with degrees of freedom, the
yes.
multiplexing gain?
Yes. So multiplexing gain and degrees of freedom is the same thing. So if you read papers, if you read the book, I use multiplexing gain, but sometimes I use DOF also. So this is also called degrees. So degrees of freedom, right? Or DOF, right? So you will see multiplexing gain DOF always is the pre-log factor of the rate. You can view this as the slope of the rate versus the SNR, as the number of interference-free streams that you can transmit. It's really important that you say interference-free, because you really see here, those streams here do not interfere with each other. C1, C2 do not interfere. That means that each of them has really a rate that looks like a Shannon expression, log 2 1 plus SNR. There is no interference there, right? Yes, so it's exactly the same notion, just different terminology. Okay, and so you will view this. We'll see this later on when we have multi-user transmission, and so you want to transmit streams to multi-user in parallel. The same concept will come in. Multiplexing gain or degrees of freedom will be how many streams can I transmit in parallel with each other without creating interference with each other. Right. Okay.
Okay. So Professor, if we don't have the perfect knowledge about the channel, so which means we cannot do the interference free for for that thing, if we don't have the perfect knowledge of the channel?
Well, yes, it's a good point. So it depends how you do the processing. Yes, so you will see here you have no interference, but you will see later on when we do the MIMO case. When we do the MIMO case without knowledge of the channels, we're going to still have the rate. Actually, the rate will be equal to something multiplied by log2. So you're going to have still a scaling factor that will be proportional to something, and we can still call it multiplexing gain, right? So the interference-free streams, the reason why I'm saying interference-free streams is because effectively to have a rate that scales as this, you need to have at some point the behavior that the streams do not interfere with. If they always interfere with each other, you will never reach a scenarios where you're going to have this. You're going to have always, you will end up with interference limited scenarios where you have something that saturates, right? So even if you don't have channel state information in the transmitter, you still have some receive antennas, and the processing at the receive antennas will enable you to separate the streams.
Okay, thank you.
Okay, so you're going to have that process, but it will not be as simple as here, because here you see that you do a very simple linear processing at the transmitter and the receiver, and then you have all those streams are just decoupled. And so what that means that you could transmit C1 using, actually, if you design a code, error correcting code, you can design an error correcting code for actually a single antenna system. And you do this 2 times. You use this for C1, you use this for C2. At receiver 1, you do C1. At receiver 2, receiver 1, you have a single antenna decoder. Observation 2, you have a single antenna decoder as well. If you don't have channel state information available, you cannot do this decoupling, and so the receiver will be a bit more complicated. You're going to have to do some additional processing that we'll see later on in order to separate all those streams. But you can still do it, right? Okay. But inside the channels, they effectively will be interfere. But once you do the processing, you can actually get rid of that interference. Right, so you're going to always have this. If you have perfect CSIT, imperfect CSIT, so channel knowledge of the transmitter, or if you have no CSIT, you're going to always, we're going to see, actually, we can write something like this. Not necessarily with rank of H, but with a multiplexing gain GS. Okay, so we'll see this later on. Probably not this lecture, but later on. Right. Right, so let's look into any other questions otherwise before we move into the MIMO channel. Right, I don't see anything. Right, so the MIMO channels, I want to give you some insight here. You will play a little bit, when coursework 3, you will play with some of those simple, statistical model of MIMO channels. But I want you to get some insight into what's happening. So when you have MIMO, multiple transmit and receive, you have the modeling of the channels becomes a little bit more complicated because you have antennas at the transmitter, antennas at the receiver, and so the directions of where the waves comes will have an impact on the performance. And so this is often referred to directionals, in the sense that you're going to have the angular distribution of the energy. It plays a role where the energy comes from. So that's sometimes called direction of departure, direction of arrival. So if you have an array like this, right, if all the energy comes from that direction like this, or you have energy coming from that direction and that direction and that direction, this will play a role. It's how much the energy is spread in the angular domain, around this array, right? And it's double because you have this at, let's say, the transmitter, but you have the same at the receiver. The receiver also, it depends on how, so sorry, that would be the receiver arriving, and then transmitter, for instance, here is how the energy departs, right? And so when you have this, you have seen in the previous modules on communication, for those in MNs, you have seen this year 3 comms. You probably have seen this again in your undergraduate modules on communication, or in maybe advanced communication theory. If you have a single transmit antenna and single receive antennas, you have you can have multiple paths, right? And those multiple paths can lead to can be the spread of those multiple paths is computed using what is called a delay spread. If you have a large delay spread, it means actually you can have frequency selectivity, right? Now, here we don't really look at frequency selectivity, but I want to give you the analogy in the spatial domain. Now, instead of having large delay spread where you have many echoes like this and coming with different delays, and so large delay spread, you can have this in the angle domain. So you can have scenarios where you have a transmitter, or let's say a receiver and a transmitter, and you have all the paths are coming in, departing into some directions and arriving into some directions, right? So your angle spread will be very small, right? All your paths actually located in the deviation around the mean is very small compared to the case where you have a receiver, you have a transmitter, and all the paths departs in many different directions and they are received in many different directions, right? So your angle spread will lead to a spatial selectivity. Your delay spread will lead to a frequency selectivity. So if I view this large delay spread, so I have an impulse response in the delay domain, and I have echoes like this, right? If I have a large deviation of those delays and the power of each of those delays, what that means in the frequency domain is that I have the response of the channels can be quite frequency selective, right? If I operate at frequency 1 or frequency 2, I can have very different behavior of the channels, right? So in this module, we don't really look much at frequency selectivity, but we always assume we have narrow bands. So always assume that we have our bandwidth is within the coherence bandwidth of the channel. But you could have that, right? So what happens in the spatial domain? In the spatial domain, if you have 2 antennas, I have an antenna here, right? Imagine it is a receive antenna, and they're spread by some distance here, right? And so you have your channel H1 here and H2, right? Coming from a transmitter, right? And so you have the channel H1 and channel H2. And you wonder how those two H1 and H2 differ from each other, right? As a function of the distance between them, right? And so if I increase the distance, I keep antenna 1, but I move antenna 2 further away, right? So I increase the distance. Well, essentially, as a function of the distance here, I'm going to have here the distance equal to 0. H2 will be equal to H1. So here I have H1 is equal to H2, right, at 0 distance. And as I increase the distance, then suddenly my channel H2 will differ from H1 and maybe something like this, right? Now, this selectivity in the spatial domain, so that means actually your channel change as a function of where you are located and how far you are from each other. That's a little bit the analogy with the frequency selectivity. So it's a spatial selectivity, it's selectivity of the channel in the spatial domain instead of selectivity of the channels in the frequency domain. And this will be related to the angle spread. So how much energy you have coming from all different directions versus having all the energy coming into one specific direction. If you have something more like this, right, all the energy comes into one direction, you're going to have something that is much more flat here, less frequency selectivity. If you have energy coming from many different directions, you're going to have something that is much more spatially selective. Similar to what we had in the frequency selectivity, if you have a delay spread where all the paths are very near to each other, you're going to have here something that is much flatter, right, over the frequency domain, right? If you have much higher delay spread, you're going to have a much smaller coherence bandwidth and so much more frequency selectivity, right? So you see the analogy between delay spread plays on the frequency domain, frequency selectivity, angle spread plays on the spatial selectivity, right? So why this happens, all those rays there, is simply because when you have a transmitter and the receiver, you have all those different propagation mechanisms. And so if I abstract all this, I can have, for instance, the base station here, and I have a mobile terminal, and those stars represent scatterers. So that means that every time I have a star, it means actually my wave that I transmit will interact with some object, will be reflected, diffracted, diffused, and will be received at the receiver, right? So for instance, here you see I don't have stars or scatterers around the base station. That, for instance, could be an example of a base station will be a high tower, right, in the middle of the city. It's very high tower, so you don't have much reflectors around that high tower. But here I have my mobile station, my mobile antennas, my handset, for instance, with two antennas. But I'm in a room like now here, and I'm going to have reflections around all the walls. So I have a lot of scatterers around the walls here, right? Now here you see the difference between propagation at the base station and the mobile handset. And that means actually if you have less scatterers around the base station, the angle spread will be smaller around the base station than around a mobile station. And so that will play a role on the spatial selectivity. And if I want two antennas, the channel of H1 and H2 at those two antennas here to be quite different from each other, independent from each other, because the spatial selectivity will be lower here because of the low angle spread, I'm going to have to spread the antennas further away from each other. On the other hand, at the mobile handset here, I have a lot of scatterers, so I'm going to have a high spatial selectivity. So I can spread the antenna just a little bit from each other, and it's very likely that H1 and H2 will behave independently from each other, right? That's the insight. That's what I want to highlight here. So that means in practice, here you need larger spacing, probably several wavelengths at the base station. Here you may need half a wavelength at the handset in order to have some form of independence between your channel H1 and H2 that you see from those two antennas. Right. We'll come back to it. Right. Okay, so our MIMO channel matrix now is NR by NT. I have NR by NT coefficients, and they have certain distribution. Each of them are random variables, and they will be correlated with each other potentially. And that will depend on the angle spread, that will depend on the distance between the elements. Good. So how can we characterize this correlation between those elements? Is by looking at spatial correlation coefficients. So let's imagine all those coefficients are circularly symmetric complex Gaussian random variables. So let's imagine I have two antennas, two transmit to receive antennas. Right, so I have H is given by H11, H12, H21, and H22. Right, and let's imagine they're all circularly symmetric complex Gaussian. So the magnitude is Rayleigh distributed. Right. Now the question is, they're circularly symmetric, each of them, but they could be correlated among themselves. Right. So how can we analyze this? By looking at this correlation matrix. So what I will do, I will look at this. I will take a vectorized form of my channel matrix. So we'll look at vec of H Hermitian. Right. So what is H Hermitian? Is H11 conjugate, H12 conjugate, H21 conjugate, and H22 conjugate. Right? What is the vec of this? Vec means actually I'll vectorize that matrix into one column. So I look at the first column and I stack up all the columns. So we're going to have H11 Hermitian, H12 Hermitian, not Hermitian, conjugate, H21 conjugate, and H22 conjugate. Right. Now I have a vector, 4 by 1 vector. Right. And I take the expectation of the product of those two. So now I have expectation of vec of H Hermitian, which is a 4 by 1 vector, with vec of H Hermitian H, which now will be 1 by 4 vectors. So I'm going to have a matrix now that this is going to be a 4x4 matrix, right? So that's going to be first entry. First entry will be this, will be expectation of H118 conjugate multiplied by its conjugate multiplied by H11, right? This will be expectation of H11 squared. That's fine. We know this is equal to 1. That's the energy that the first channel gained, right? Now, if you have entry 1, 2, what is the entry 1, 2? Is this one, expectation of H11 Hermitian, by the second entry, when I do the transpose, by this, right? And I take the conjugate because of this, right? That's H12, right? If I take entry 2, 1, I have entry 2 is 1, 2 Hermitian, and the first entry is H11. It's there, right? And so on, right? So what you see here, what does that mean? This quantity here. I'm looking at H12, H11 and H12. So if I have my transmitter, my receiver, this is H11. H12 goes from the second antenna, transmit antenna, to the first receive antenna. So that's, oops, sorry, let me take another page. Oh, yeah, so so I have receiver, transmitter, so this is H11, this is H12, right, going from antenna 1, antenna 2 to antenna 1. Right, then I have, let me change color, that will be clear. This is H12. I have this and I have that. This is H22 and this is H21. Okay, so now I'm looking at this. H11 with H12. So I'm looking at this one with H12, which is this one, right? So I'm looking at the same receive antenna. The first index is 1. So I'm looking at the first receive antenna. And from the first receive antenna, I'm looking at the correlation between those two channel gains, right? So that will tell me from the first receive antenna perspective, how those two channels actually relate to each other. Are they correlated with each other? How much are they correlated, or are they completely uncorrelated, right? And you can do this. You're going to have a 4x4 matrix here, and that will characterize essentially the correlation between any of those 4 coefficients. The diagonal entries here will be always equal to 1, right? Because all those channel gains have the same energy, but the correlation will change. So I'm going to have, for instance, this is, you can view this as a form of transmit correlation. So it's a correlation between 2 channel gains from 2 different antennas. I could have something else. If I look at the expectation of, what do we have here? H12 and H22 conjugates, for instance. Right. So now I have the same transmit antennas, is 2, right? And I'm looking at the 2 channel gains at the 2 receive antenna, antenna 1 and then antenna 2. So this will actually tell me a form of receive correlation, how much the antennas are correlated at the receiver when I look at them from transmit antenna 2. Okay, so this is what is denoted here in this matrix. You have T is the transmit correlation, you have R is the receive correlation. T1 is when you look at transmit correlation from from receive antenna 1. So this here will be transmit correlation 1. I look at from antenna 1 the correlation between those 2 coefficients. So it's a correlation between those 2 antennas, but from receive antenna 1. Receive antenna 1, sorry, this is not T1, T1 is there, right? This would be here, what would be this here is receive correlation, is a receive correlation, because I'm looking at the correlation between those two antennas, 1 and 2, from transmit antenna 2. That's receive correlation 2. Okay, so all those elements can be characterized into this matrix, and the S here is the correlation between those diagonal entries. For instance, that was the correlation between this element and this element. Right? They don't have the same row, they don't have the same column. Right? So it means that I'm looking at the correlation between this element here and this one, for instance. Right? You see, you can have a lot of different coefficients to compute. Typically, T1 and T2, whether you look at from the first receive antenna or the second receive antenna, you can say in practice T1 is equal to T2, same as R1 is equal to R2 in practice. So whether you look at from receive antenna 1 or receive antenna 2, you look at the correlation, it will not change much because the distance is relatively small. As long as the distance is small, it will not change too much, the statistical properties. Good. So so we'll see later on. There are actually models to simplify this, because now you have quite many different quantities. So if you assume this and assume that, you can already reduce the number of coefficients, and you can show that actually S1 and S2 can be written as a function of T and R as well. So ultimately, we're going to have a model later on that will be only a function of two coefficients, T and R. T will be the transmit correlation coefficients, R will be the receive correlation. So it tells you how the transmit correlation coefficients are actually, the transmit antennas are correlated with each other. So how the channel gains at the different transmit antennas are correlated with each other. And R will be the same, but at the receiver site. Right. Okay, so now whether we look at T or R does not really matter. I want to show you how these behave as a function of the angle spread and the distance between the antennas. So let's imagine that I have simply a scenario where I have a single receive antenna, right? And I have two transmit antennas, so antenna 1 and 2. And I have a certain distance here, dt between two transmit antennas. It's the same if you have the opposite, which is you have a receiver with two receive antenna, one transmit antenna, you could have a distance there as well, right? The same can be applied to that scenario, right? But let's assume here, in just for the sake of fixing the notation, that I'm looking at two transmit antennas, and I'm looking at spreading of dt. So we're going to look at two scenarios. The first one is when I have a lot of scatterers, that is called isotropic scattering. So it means that I have a lot of those stars that I had earlier on. They're all everywhere here around that array. And so that means that the wave that I receive at the receiver will travel through these scatterers, will be reflected. And I'm going to have many of them, right? From each of those transmit antennas, they will go and be reflected, right? Many of them. So in other words, if I have isotropic scattering here, my angle spread around the transmitter is very large, very large. And so what you can show is that your transmit correlation coefficient then, and all the details is in the book, right? But this is way too detailed. We don't go into this. I just want you to understand get some insight and see what's happening. So you can show that the transmit correlation actually write as a Bessel function. That is a function of your distance. If you have large scattering, you have that as you increase the distance, the argument will be the distance between the two antennas. And so if you think about the Bessel function, it is something that actually is decreasing as the argument increases, but you have some form of fluctuation, right? So let me show you right away what this is. This is your Bessel function here, this one. And so you see that that's the distance, that's your dt, but relative to the wavelength divided by lambda. So this is what we have here, is divided by the wavelength. So it's relative to the wavelength. And so what you note here is that, well, the correlation coefficient decreases very quickly, right? Very quickly with the distance, and then it oscillates. But roughly, if you have a distance of roughly 0.5 wavelength, you have a transmit correlation coefficient that is relatively small, less than 0.2, 0.3. Right? So what that means that if you have isotropic scattering like this, many scatterers around your array, and you spread the antennas by 0.5 wavelength, your two channel gains here, seen from one receive antennas. So here I have if I abstract this, I have receiver, and I have H1 and H2, right? And H1 and H2 comes from the sum of all those paths, the contribution of all those paths. But because I have a large angle spread, H1 and H2 will be quite uncorrelated with each other if the distance is larger than 0.5. So that's good. That means that if I want to do Alamouti, for instance, or if I want to do maximum ratio transmission at this transmitter, and I want to have a diversity gain of 2, I want to remember that we need to have H1 and H2 to be independent from each other. If they're actually the same, I will not have a diversity gain of 2, right? So to have a diversity gain of 2, they have to be independent. That means actually roughly they have to have a spacing that is larger than 0.5 lambda. The antennas here will have to be larger than 0.5 lambda. At 2 gigahertz, what that means is half a wavelength is 7-8 centimeters, right? So handset, you need to have antennas roughly at 7-8 centimeters in order to have those two channel gains to be independent from each other, right? And to really benefit from diversity. That's what it means. Right. Really handset, because the handset is typically surrounded by many scatterers. Now, what if you have the opposite, highly direction scattering? So highly direction scattering is the opposite scenario, is where opposite in the sense that you still have one antenna, you have two transmit antennas. But no, you don't have all those scatterers. You have all those scatterers, they're all there in just one direction, right? Not surrounding, not isotropically surrounding the transmitters, but they're all into one direction, right? And that direction is given by this, right? So that's my direction. So they're all into a certain direction that is given by this. I could have a direction like this, right? All in direction like this and like this, that's okay. But they're all into one direction. Right? So what's happening there is that you have your correlation coefficient now is written as something like this. The magnitude is equal to 1. So irrespectively of the distance, the magnitude of the correlation coefficients is equal to 1, right? So that means that if you put all your scatterers into one direction, you don't have, nice spreading around the transmitter. You're going to have your correlation coefficient will be flat, whatever the distance between the antennas. And this is a problem. If it's flat, it means that you are here, right? If the magnitude is equal to 1. Increase the distance, it does not matter. The correlation, the two coefficients are always fully correlated with each other. So if you increase H1, H2 will increase, right? So you're going to have really a linear relationship between H1 and H2, right? You're going to have zero diversity gain. The diversity gain will be equal to 1. Will be the same as if you have only one antenna in terms of diversity gain, right? And now if you have something that is in between those two extremes, so you have some spreading of the energy, is, for instance, something like this. You have a transmitter, and you have some spreading of the energy goes into these directions, right? Something like this, right? So around that direction, not all around, but you have still some angle spread, right? Here you have zero angle spread. Here you have very large angle spread over 2 pi. Here you have something that is in between, right? And so if you have something in between, what happens is that you have this K2, K10, K100 and K500. As you increase this K value, essentially you go from something that is very isotropic to something that is very directive, right? In other words, as you increase this K, you decrease that angle spread here. You decrease the angle spread here, right? So as you decrease the angle spread, you see that your correlation coefficient for a given distance will increase, right? So if you decrease the angle spread, you decrease the number of scatterers you have around this, this array. It means that to guarantee a certain correlation coefficient between the two antennas, you would have to go for larger spacing between the antennas. If you want to guarantee 0.5, if you have a large angle spread, it's okay, you can operate here. If you have very small angle spread, you have to operate at much larger distance. This is what you have typically at the base station. So at the base station, you have to spread the antennas further away because the angle spread is smaller, and so you need to have a larger antenna spacing in contrast to a mobile. So maybe this is more relevant to a base station. This one here would be more relevant to, I don't know, a user equipment, for instance, right? So it depends a lot on the applications. Like if you have satellite, if you do MIMO over satellite, where you have line of sight with your satellite is a bit like you have something like this, right? So there it's very difficult. You're going to have to put the antennas very far away from each other in order to try to have some different behavior. Okay, so that's the main idea that I want you to understand. Now, yes, any questions?
Yeah, Professor Bruno, I want to ask, what do you mean by the parameter k? Because you mean what is exactly the physical meaning about the parameter k in this figure? Because you say that k equals to 0 is kind of isotropic scattering, and if k is like equals to the infinity, it becomes the directional scaling.
Yes. So k, I mean, to go into the detail, you have to see the distribution. The k comes from a distribution that is explained in the book. But here you can view k simply as angle spread. Simply. So if k is equal to 0, it means that you have an angle spread of 0. So that means actually all your path departs from the same directions, one unique direction. If k increases, it means that your angle spread increases, right? And k being very large would mean the angle spread equal to pi. So there is a kind of direct relationship, if you like, between k and the angle spread. That's what it means.
Okay, so I guess if we increase the k, it should be decrease the angle spread. If we increase the k.
Sorry. If you increase k, you decrease the angle spread. Yes.
Yeah.
Sorry.
Yes.
So, yeah. So k increase is equivalent to saying your angle spread decrease. Right. K decreasing means your angle spread increase. Right. So here I can say this is small angle spread, and here this is large angle spread. Right? Sorry if I said the opposite. I think you understand, right? Large angle spread is small k. Small angle spread is large k. Right? Okay?
Okay, thank you.
Right. Right, so key is if you have small angle spread, you need to have large spacing between the antenna to achieve a certain correlation coefficient. If you have a small, and inversely, essentially. Right, so so that two. So the simplest way to model this R is something we have seen already. Is when you have IID relay fading. So now you assume that all those channel gains, all those 4 channel gains we had here, for instance, they're all independent from each other. So all the correlation, they're circularly symmetric complex Gaussian random variable, and they're independent from each other. The correlation coefficient is equal to 0. In that case, what happens is that your matrix R here will be just an identity matrix, right? That's the simplest scenario. What does that mean physically speaking? According to this, if you want to have 0 correlation, it means that you have to operate here, right? 0 correlation in magnitude is 0. So you need to have large spacing and large angle spreads, right? If you want to have really 0 correlation guaranteed all the time. Large spacing, large angle spread typically, right? If you have a large angle spread, you could have relatively smaller spacing, but typically is you have to increase either the spacing or the angle spread as much as possible. So this is a very simplistic model, but it is good, right? This is what we have used essentially before when we calculate diversity gain and so on, is always assume you have independence between those channel gains. If you have correlation, your diversity gain will decrease. Now, in reality, you can imagine you don't have this because your spacing is not sufficiently large or your angle spread is not sufficiently large. So you're going to have typically some correlation among those antennas. So you can have limited angular spread, or you can have reduced array size, or you could have something that is not even really distributed. So you don't have circularly symmetric complex Gaussian random variables. You have something that a bit more complicated, is modeled using Rishon distribution. And you can see this in the book if you're interested. Essentially, it means that you have a line of sight, and on top of this, you have reflections on buildings. And so the reflection will create some fluctuation of the received signal, but the line of sight will be quite stable. And so because of this, you're going to have a slightly different behavior than if you have just really fading. And then you can have multiple polarization as well. So what I talked about is mainly when you have the same polarization for all antennas, but you could imagine that you have different polarizations. So some antennas use vertical polarization, some other antennas use horizontal polarization. So if you take a system like 4G or 5G, in 4G you can have up to 8 antennas, and what is typically used is this, right? So if you have 8 antennas, you have 4 antennas that are polarized by 45 degrees, and 4 antennas that are polarized by minus 45 degrees. And the reason why you do dual polarized antennas is because you can pack all those antennas closer to each other. The 2 antennas here, they're on top of each other because they have different polarization, orthogonal polarization. Actually, you can view it roughly that actually the channels will be uncorrelated, right? If you have this, something like this can also be used, less popular than this. Then what happens here is that your array may have a bigger size because you have single antenna, single polarization. They're all vertically polarized, but then they actually the array size can be bigger, right? If you go to 5G, you're going to have those antenna patterns could be something like in 2D. So you're going to have maybe antennas like this, right? So those are so I have 24 antennas here, 12 that are actually polarized like this, 12 like this, 24 antennas that are located in a panel that spans horizontal directions and vertical, right? So that's typically what you could experience. Good. So how can we model then channels that are correlated, right? They're still really distributed. That's what we're going to assume in all this course. That's what you're going to assume in the course all the way to coursework 3 as well. But they can be correlated. And so how you generate a correlated vector from independent vector. So you assume your vector here, the entries are CSCG. So they're all circularly symmetric complex Gaussian random variable and independent from each other. So IID, right? And you have a vector of them. So if I have a 2x2 matrix, and I want to generate correlation among those 2x2 entries, those 4 entries, I vectorize it. So from 2x2, I get a 4x1 vector, right? I generate IID vector here, IID CSCG IID vector. That's what I have here. And then I multiply by the square root of a correlation matrix. And what I'm going to end up with is actually a vector of no correlated entries. And so you can map those entries again to your 2x2 matrix. So once you have this vector here, you can map this again to this 2x2 matrix and get your 2x2 matrix, but that are correlated. Okay, so you will play with this. You will use this in the classes and in the coursework 3. You will use that. So how do we model R? Well, you could put R. You could choose that, for instance, here. What we had here, sorry, where was it? This one. but then you have lots of coefficients, right? So a simplified model of this, of R, is given by this here, where you have a Kronecker product between a receive correlation matrix and a transmit correlation matrix. So what is a Kronecker product? Is the following. Imagine that here, what I do, I have two, let's take this example. I have a 2 by 2 matrix, and I have two of them. And by Kronecker, what I do is that I take the first entry, right? And the first entry is multiplied by the entire second matrix, right? So from one entry, I now go to a 2 by 2 matrix here. So you see this one essentially comes from this multiplied by this matrix. This one here, this block here, comes from the second entry multiplied by this matrix. So I have R conjugate multiplied by this matrix, right? So if you have a 2 by 2 and you do Kronecker products of 2 by 2 matrices here, you're going to get with 4 by 4 matrix because each entry has been multiplied by the second matrix. And here you have this entry here that is multiplied by this entire matrix and so on, right? Now you see here you have only two correlation coefficients. You have the receive correlation coefficient and transmit correlation coefficient, right? And so this is one model that says, well, your total correlation matrix essentially is just a function of a receive correlation matrix, transmit correlation matrix, and it's just a function of two coefficients. Receive correlation, so correlation coefficient at the receiver side, correlation coefficient at the transmitter side. And all those T1, T2 actually are equal to R here, or T. And S1, S2 will be simply equal to the products of R and T, right? So this is a very simple model that is been used quite a lot in the MIMO. This is what we're going to use in coursework 3 as well. And so you can fix a certain correlation coefficient, for instance, for the user at the transmitter side, or the base station, and from there you can generate a 4 by 4 matrix. Once you have this 4 by 4 matrix, you can generate many IID vectors like this. You can multiply them together, and you're going to get a vector of correlated entries whose correlation is in line with this, what you have fixed for T and R. Okay, and so if you change the value of T and R, you will see the performance will change. Right, that's what it means. So if you have a correlation matrix that is equal to the Kronecker product of RR and RT, so the transmit and receive correlation matrix. So that's called Kronecker for those who actually have never seen this. The definition is actually here, if you want to know more. But this is exactly what I just described already. So if you go to some of the reminders here, right, you have the Kronecker products. Right, so you take any entries of A and you multiply by B, essentially. Right, so you're gonna get a very expanded matrix. And you have some properties of Kronecker products that are given here. Not sure we're going to use them much. That's essentially the main thing that is important here. Right, so so once we have that, then you can generate your correlated entries. And then depending on T and R, you're actually going to have a different performance. And so if you have a Kronecker model of R, what it means physically, it means that your channel matrix H can be written as follows. You have here, this is an IID matrix. So the entries here are circularly symmetric complex Gaussian random variables, and they're independent from each other, right? And you have a receive correlation matrix and a transmit correlation matrix. If you have a correlation matrix R that is given by the Kronecker product, it means that your actual H matrix can be written as IID matrix multiplied on the right side by the square root of this correlation matrix here, RT, and on the left side, the square root of the correlation matrix RR. So you will use that in the class and in the coursework. You will see how you can generate this in MATLAB. Right. Right. So probably you have seen this in how you generate this in class 1 already. Right. If you do rand n plus j rand n, right? You're going to get circular symmetric complex Gaussian random variable. Those two will be independent from each other, right? And you may have to normalize by square root of 2 in order to have the variance equal to 1 here, right? By default, this will be a normal 0, 1 in MATLAB. Right, so you can do this, you can use that to generate vectors, and from there obtain your matrices. Right, so in the coursework 3, you can fix your correlation coefficient, you can change it, and you will see from there how your rates performance will actually change for the specific communication scheme that you will play with in coursework 3. Right, so that's about the basics of MIMO channel modeling, and you will become more familiar with this once you start playing with that. Now, what I want to do now, just to introduce, is capacity of MIMO channels. So now we're going to go back to what we had earlier on. We had this sum, and we had this power allocation problem. Now we're going to try to understand, oh, how can I actually design this power allocation, right? That's under the assumption that I have perfect CSIT. I know the channels of the transmitter. And then we're going to look at what's the capacity when I don't know the channels of the transmitter. And then we're going to revisit what we did for the single antenna case. We saw slow fading, fast fading. We're going to see what happens in the context of MIMO. Right, so this is just a reminder of what we saw already. So this is the system model we're going to play with. I have CK prime, which can refer to different things. But essentially, I have this prime here to highlight that this could be actually some form of pre-coded vector, right, or pre-coded information. What we had earlier on, we had CK prime, for instance, could be something like this, where I have VH multiplied by C, right, when I do the multiple eigenmode transmission. Right, the system model remains the same, and what we're going to see is that a lot of the performance here are going to assume when we look at the rate, we're going to always think if I have rate Shannon expression, it means I have Gaussian signaling. That means actually I have Gaussian input, and I can actually compute, because I have vectors now, I can compute a covariance matrix. So a lot of the rate expression we'll see will be a function of the covariance matrix of the input. And this covariance matrix will actually be a function of this kind of pre-coding that I may have when I have channel state information at the transmitter. I know H at the transmitter. So we'll see this in a minute exactly what that means. And I have a power constraint here of this covariance matrix. That means actually the trace of this is smaller or equal to 1. It simply means that I always constrain my power at the transmitter so that whatever number of transmitter antennas I always compare with the same power level, so to maintain to compare apples to apples, essentially. Right, and then we're going to have slow fading and fast fading, same as what we have seen in the SISO case. Right. So first scenario, let's look at deterministic MIMO channels. So deterministic, I have a channel matrix H, does not change over time, and the question is, what's the maximum rate that I can convey over these deterministic MIMO channels? And so under the assumption of having AWG noise, right, is completely IID across the different antennas, you can compute your rate by essentially a maximization of the mutual information, right? So here I will not go into the information theoretic part, but if you're interested, this is explained in the book. You will see where actually this expression comes from, and then you have more details exactly by relating the mutual information with the entropies, calculating the entropies of the source and the noise, and you will see exactly how you get this expression. What I want you to understand here, what does that mean? So here we have a mutual information which is equivalent to what we had in the SISO case. In the SISO case we had this, right? 1 plus SNR. Right, and this is with Gaussian input. So here I assume still I have Gaussian input. So my C here, C prime, are Gaussian distributed. They have a certain covariance matrix now that comes from the fact that I have multiple antennas, right? So that covariance matrix is something I can choose. So here I use Gaussian input with a certain input covariance matrix, but this achieves a certain rate that is measured in terms of mutual information, and it is given by this log2 determinant of this quantity. So if you think about what you have in SISO case, this quantity is 1 in size, so you have one receive antenna. H here is just a scalar, right? Q is just disappears if you have one transmit antenna, so you're just going to have 1 here. The trace of a scalar will be equal to 1. And then you have your long-term SNR as always, right? So this in the single antenna case, in the SISO case, is essentially, and the determinant of a scalar is just that scalar. So I'm going to have log2 1 plus rho h squared. This is exactly what we had earlier on in the SISO case, right? If I have SIMO case, I have here an identity matrix, and here I have I'm going to have a vector here, right? And here I'm going to have a columns. And I have a SIMO case, I have a single transmit antenna, so my Q will be equal to 1 again. So what do I have then? I have a log2 that I and R, I have R receive antenna, rho, H, that's a vector, multiplied by H Hermitian, right? What is that? This is log2, 1 plus, I can change the order here. So the determinant, if I change the order here, this is actually the same as the determinant. Let me do all the steps. This is the same, I think this is the determinant. If I change the order, 1 plus rho h Hermitian h. Determinant of a scalar is just 1 plus rho h Hermitian h is the norm of h. Okay, so this is a little trick here. This has only one singular value, so you can always change the order here. I can show you some properties. I think we have this here of this log2 det. I'm going to use this changing this order a few times, so you're going to get familiar with that. I think we have this here. Here, right? So determinant of I plus AB is equal to the determinant of I plus BA, right? Careful, the dimension of I here and there is not the same, right? This is exactly what we did. We had I here is equal to an R dimensional, and then the I in the next step is actually equal to one dimensional, right? So here, if I have this A is a vector and B is a vector like this, right? And I is an R dimensional. If I switch the order, now I have a vector like this multiplied by this is going to be a scalar, and so my I here will be a scalar, right? And so determinant, no, a scalar would be simply that scalar, right? It's exactly what I have just used. Okay, so again, your expression here of the MIMO case boils down to what we have in what we had in the SIMO case. Right, and you can do the same for the MISO and so on. So the MISO will be a function of Q now, that I will explain in a minute. Right, so this is a function of Q. So if you want to get the maximum rate, the capacity is the maximum mutual information. Well, you take the maximum over any probability density function of the input. Here we know, because we have Gaussian noise, the optimal input distribution is Gaussian distributed, but the covariance has to be chosen. And so that's why here, now I maximize over the covariance matrix of these Gaussian inputs. And so I have to find the Q that maximize that quantity. Okay. How we do that, we will go back to what we did earlier on, this module, not this module, this lecture, where we were pre-coding along VH, like here. And now we'll see that if you do that, essentially, you will end up with a covariance matrix that will be related to this V of H. And we'll see that actually doing that will actually is what will maximize the capacity. So we're going to relate the multiple eigenmode transmission with the capacity achieving strategy. So I will stop here today, and next week we're going to start looking into that. Okay. As usual, any questions, let me know, or discuss with the GTAs as you wish. And I see you next week. Thank you. Bye-bye, everyone.
Bye.